Okay, hello everyone. This is Shuguang from Grab, the lead data engineer from data ingestion team.
And this is Shikai, also software engineer from Grab.
Yeah, so today we're gonna talk about enabling the real data lake in Grab, and we are gonna show how we are running those pipelines and the impact in the Grab. So here is the agenda today. First, we're going to talk about challenges with the conventional CDC using Hive tables. And that's something implementation we doing back in 2022. And the second item is the reason and the high-level architecture that we transit to the Flink CDC with Hudi. And the third item is the data freshness to monitor the Hudi table we built in Grab. And the fourth item is the self-service journey in Grab, since it's a lot of components involved in running the Hudi tables. And the fifth one is the use case we have in the fraud team in Grab. Yeah. So back in 2022, Grab implemented a CDC ingestion with Hive tables, a system compromising various components to synchronize data from online sources to offline data lake. So you can see that in the graph we have the DBZM component, the Kafka message queue, as well as the Grab in-house tool like the archiver and the compaction job that to transform the data into a Hive format, which is efficient for query for users. This architecture aimed to address two primary issues back then. The first one is the inconsistency resulting from the double writing, and the second one is the high CPU load experienced by SQL-based pipelines. Following this deployment, the architecture gained widespread acceptance among Grab's business teams. However, over time, we began to recognize there are certain limitations in this design. The first limitation is we cannot achieve better freshness with Hive tables. So the best freshness we can achieve by the Hive table is 1 hour. And this is due to two reasons. The first reason is like the data only sync on an hourly basis. And updating the Hive tables is quite costly as well. So even if we want to run more than 1 hour, more frequently, like less than 1 hour, it's too costly that we need to rewrite the whole partitions for each updates. So this makes this more fresh and practical in the tech, from a tech view. And the second bottleneck we encounter is the cost of maintenance. So in the previous design, we need to upkeep a Kafka Connect cluster and a Kafka cluster as well. And also, since we are maintaining the in-house logic for observing the bin log events to Hive tables, so there are a lot of engineering efforts to be there. Yeah.
So moving forward, we've actually simplified our design to reduce the number of components within the system. We've still adopted DBZM CDC. We are using Flink CDC, which wraps around the DBZM engine with the Flink wrapper. With that, the Flink pipeline is actually able to treat the MySQL bin log stream directly as a source instead of relying on a Kafka topic to ingest it into the data pipeline itself. That's the first change we made, which is to adopt Flink CDC. Subsequently, we also made a change to change the table format from Hive table format into Hudi format. So as we move to adopt the Hudi as a table format to solve the challenge on data freshness, we are able to ingest the binlog stream as a DBZM source records before transforming them within our pipeline into a Hudi records. In this transformation process, we have also injected various metadata and also instruments various monitoring systems to detect the latency and other metrics associated with the transformation process to guarantee a certain SLA to our data consistency and data freshness that we provide. So these transform records are then sent into our Hudi data lake on S3 cloud storage during the Flink checkpoint operations. So at each checkpoint operations, Flink will actually commit the files onto S3 by writing the files and completing the multi-part upload. As also part of the checkpoint operations, Flink will also create the relevant commit files into the metadata file of a Hudi timeline. So for merge on read tables that require additional table services such as compaction and cleaning, an additional Spark job is also created to run these table services on a periodic basis. So by simplifying our architecture in this manner, it allows us to actually perform multiple ad hoc operations such as cold start recovery or bin log offset resetting in a much more manageable manner. Previously, such operations require support to change Kafka topics, also changing Kafka Connect configurations so that it recognizes the new bin log offsets, downstream and scaling of the downstream Spark jobs for the operations due to the ad hoc load spikes. So as compared to these operations before, scaling up and managing a single Flink pipeline is a much simpler operation overall. So if we zoom into the Flink pipeline setup, we will first split the design into two different forms of Hudi tables, merge on read and copy on write. Because based on these table formats, the operations that Flink pipeline would do would differ slightly. So firstly, for the copy on write tables, which are much more simpler to ingest, at the end of each Flink checkpoints, the packet files will actually be directly written onto S3 and a corresponding timeline commit file will also be committed into the metadata timeline at the end of the checkpoint. So this metadata timeline refers to the Hudi metadata timeline that's preserved in S3 also. So since such pipelines do not normally require heavy compaction table services, we run the table services that includes the archival services and the cleaning services asynchronously within the Flink pipeline itself. So there's no need for a separate Spark job, in this case for copy on write tables. However, while simple in design, copy on write tables do not actually satisfy every single requirements we have. For example, copy on write, we can't really improve the data freshness for copy on write tables based on the fact that copy on write tables are writing the data directly as Parquet files, which is an expensive operation. By actually trying to improve the data freshness, we would inevitably reduce the checkpoint interval, so increasing the checkpoint frequency. We actually increase the amount of write operations we incur, and hence the amount of resources that we need to provide just to make the data fresher. So in a lot of scenarios, this would be simply too costly for us to run on a long-term basis. So another downside of copy on write table is that because each writing of the Parquet files is expensive, the limit in the throughput that it can serve, there is also a bottleneck to it. And for large throughput topics or large throughput of data, copy on write tables may not be suitable for such scenarios. So then, what we will do for such scenarios for large data throughput to provide a higher data freshness guarantee, we'll actually use merge on read tables. And so for merge on read tables, the Flink pipeline will actually output the files as log files in Avro format, which is cheaper to write. So at the same time, the Flink pipelines will also generate the compaction plans and commit them into the Hudi metadata timeline. So a separate Spark job will also run separately to run the actual compaction operation. So this compaction operation is expensive and will actually be a very spiky workload, and that's why the Spark job is created. So by having it set up this way, whereby a Flink pipeline is actually doing the compaction plans at the same time, we are actually avoiding the issue of concurrency writers, because essentially it's still a single writer setup. The Flink is writing the log files and also generating the compaction plans. The Spark jobs is just acting on the compaction plans generated and taking the relevant log files and combining them into a final Parquet files. So additionally, this setup also allows us to separate the operations of different load pattern, whereby the spiky compaction load is separated into a Spark job and the relatively constant data ingestion load pattern is done by the Flink. So overall, we monitor the data freshness of our end Hudi table via Trino, and this whole platform, that the screenshot UI that you see here, is actually our internal portal to do so. So by comparing the timestamp of the latest MySQL upsert with the most recent record available in the data lake, we can measure how closely our Hudi tables reflect the source data. We perform these checks every 20 minutes, with 99% of the test executions showing a freshness of under 20 minutes, which is our current SLA guarantee. However, it's worth to note that actually 86% of the tests indicates that the actual freshness is actually under 10 minutes. Meaning actually, although we promise 20 minutes, we'll actually be able to deliver much fresher data under 10 minutes or so. So, however, a limitation to this is that actually Spark would running this check on Spark will actually provide a more accurate measure of freshness due to its ability to support snapshot queries on merge-on-read tables. We primarily use Trino as it aligns with the majority of our users' workflow. However, Trino has a limitation whereby it can only read the Parquet files. So for merge-on-read tables, we are actually hitting much fresher data latencies, but since the log files are ignored, they can't really show up in our checker here. So one challenge in achieving this optimal freshness with Trino is precisely that, whereby it only supports reading Parquet files. And to actually make our merge-on-read tables fresher according to our users' usage of Trino query engine, we ended up having to shorten the compaction interval to generate more compaction plans. And we frequently compact these Avro log files into Parquet files.
Yeah. So this graph is showing the journey that we move from menu onboarding to the self-service journey. So in the initial setup, you can see that the data users need to raise data ingestion pipeline to the data ingestion request to the data engineers, and who has a knowledge of Hudi and stuff, and they need to manually spin up the Flink ingestion pipelines and Spark table services if needed, MR table, and perform Hive registration, and create the corresponding data quality monitors, which just now you see, which is called Genji. And we have subsequently tried to automate these operations because it's really taking long, like 1 day for one pipeline. So we want to automate the thing to make the ingest pipeline easy for users and to scale for the business. So, and below I'm gonna talk about the step how we onboarding the Hudi tables with self-service. So firstly, we're gonna derive the associated RDS schema from the binlog stream with the DBZim engine, and we need to register this as an Avro schema with the Hudi table in our backend. And secondly, based on the configured data sources such as RDS size and IO ops, we are able to automatically provision the resources like Flink or Spark to be created. And we also derive the application config such as RDS configuration and RDS table by just a user click and drag to get those RDS informations. And in our current setup, each Hudi tables would have a dedicated Flink pipeline running in their own Flink cluster because of the proper resource isolation can be achieved. At the start of each table creation, a snapshot operation will be conducted to build a whole table, which will take a full snapshot of target RDS. This operation requires actually higher resources due to its associated larger data load from ingestion the data. But at the end of snapshot, the pipeline will switch to the CDC mode and only reading the bin log, and this requires less volume. So we also tune this config automatically when we see that the pipeline is changing from snapshot to the incremental mode, reading from bin log. So all these operations are orchestrated behind the scenes by our ingestion platform, which is called with Temporal. So for MOR tables, the table services is activated as soon as the Flink pipeline finishes writing the first data files. We have a background process that continuously monitoring this. And given the timing of compaction and cleaning operation is crucial for ensuring the stability and the cleanliness of files in Hudi, we also have automatically derived the frequency of Spark compactions. And the Spark compaction normally will be slightly more frequent than the compaction plan ingestion, because in this way, we can guarantee that all the compaction plan can be processing timely and without any issue. Regarding cleaning, the frequency is determined by the archiving frequency and designated lifespan of the files. So this frequency is also automatically derived. So for copy and write table, it's slightly simpler because we run all the table services directly in the Flink engine as inbuilt services. And this approach eliminates the necessity of offloading the computation task to the Spark engine. So at last, we will register Hudi tables as well to the Hive store. But there's one issue, like the trainer need to preload all the metadata to make the query speed. So nowadays we find that trainer queries are slow because it need to load all the metadata. So that's why we run the Genchi platform to run the test case every 20 minutes to warm up the metadata to speed up the query. So next slide, please. So the last slide is about use case. So a sample use case of how Hudi are used in Grab is a fraud detection. So actually fraud detection is an operation characterized by its need for real-time data as well as the ability to run ad hoc queries on production data sets. So any delay in detection of fraudulent transactions will be quite costly to the organization, especially when we are facilitating a large volume of transactions via our marketplace. So although running Hudi pipelines will be more costly than running Hive pipelines, but the gain we get from this in-timely fraud detection will pay us off. So as such, near real-time data lake will satisfy their requirements. The data lake provides a scalable buffer for team to run ad hoc queries on without any impacting production systems. And the low latency nature of the table would allow the analysts to work relatively fresh data. So today, our fraud teams are able to analyze transaction data such as payment trends with data freshness less than 20 minutes, allowing them to quickly analyze and push new detection models in response to any new threats that's servicing our marketplace. Yeah, I think that's all about today's sharing.
Yeah, thank you.
Thank you.